All right, here's a second example of solving trig equations. How about 3 tan x minus 4 equals 0? So similar to the last one, this is very much like a linear equation at first. You add the 4 over the other side. 3 tan x equals 4. Divide by 3. Tangent x equals 4/3. I now have to figure out what x is. You know, I've seen a lot of people do this in the past, and this is completely wrong, so do not do what I'm about to do. But I've seen people do this and say, well, I'm going to divide both sides by tan. So they have 4 over 3 tan. And it's like, what? What the heck is tan? I mean, the name of the function has no value. It needs an input in order to give you an output. So this is just completely... Yeah, that's what I think of it. Just don't do that, okay? How do you get an x out of a tangent? You have to do an inverse tangent, right? So x is the tan inverse of 4 over 3. Now, if this happened to be a nice angle, so I'm looking at this saying tangent is the opposite side over the adjacent side, with the opposite side being longer. 4 over 3. Oh, this is my 3, 4, 5 triangle, but anyway, x is this angle, right? Or I could be down here where this is -4 and -3. Right? My calculator, when I grab my calculator here and ask it, you can't see this anyway, so I'm going to put it off to the side here. I say tangent inverse of 4 divided by 3, and I've put myself in radian mode, so it gives me an answer in radians. It's going to say x is 0.927295, whatever. Okay, that's this angle right here. That's in radians, a little bit less than 1 radian. But that's not the whole picture, right? There's two things going on here. One is there's something down in the third quadrant, and then there's anything coterminal with either of those two angles. But with tangent, one of the things that's kind of nicer than sine or cosine is the tangent repeats every pi, where the sine and cosine repeat every 2 pi. So in order to get from here to there, I'd have to add on pi, right? Pi radians. To get around to there, you'd have to add on another pi, and then another pi, and another pi. That I can describe actually all of these angles by saying x equals 0.92729 plus just pi n. And I'm always using n to represent an integer. So 1, 2, 3, 4, or 0, or -1, or -2, -3, so on. This was not a nice angle. So anyway, the calculator just gave it to me with inverse tangent. Okay. Let's do another example. How about something like this? How about the sine x times the cosine x equals the sine x? It's a very tempting thing to do here. I've seen people do this many times. They divide both sides by sine x. And they get cosine x equals 1. Well, I mean, they're going to get solutions to that, but you've just lost information. You've just, you've possibly divided by 0 because the sine of x might be 0. And in fact, if the sine of x is equal to 0, this would be a good thing because you'd have a 0 on this side times cosine, you'd have a 0 on that side, and you'd have 0 equals 0. So you're losing solutions if you divide both sides by sine x. Instead, let's subtract the sine x over to the other side. Sine x times the cosine x minus the sine x equals 0. Then factor the sine x out of this. This is sine x times cosine x minus 1 equals 0. And now I'm in a situation where I've got a product equaling 0. Products equaling 0 are nice because there's only one way. Well, of all the ways that you can make a product equaling 0, you know that every time one of the two things you're multiplying is 0. That's not true about any other number. If you've got two numbers that multiply to be 7, right? A times B equals 7. What does that tell you about either A or B? It doesn't tell you anything. Sometimes people say, well, one of them's 7 and one of them's 1. It's like, how how about 14 times a half? Right? That's 7. Or how about a million times a million divided by 7? Right? That's 7. That is, if it's equal to 0, sorry, if it's equal to something other than 0, there's nothing you know. But if a times b equals 0, then either a equals 0 or b equals 0. There's no other options. So here I've got a product equaling 0, so I know that either the sine of x equals 0 or the cosine of x minus 1 equals 0. So where I had one equation that had both sines and cosines in it, by factoring like this, getting everything on one side, 0 on the other, factoring, I have two simpler equations now, each of them involving only one trig function. So when is the sine of x equal to 0? Oh goodness, in that one I would look at a sine curve and say, when does that cross the axis? It crosses here and there and there. So it looks like x equals 0 or pi or 2 pi. Actually plus or minus pi or plus or minus. So I think an easier way to say that would be x equals n times pi, right? All of the integer multiples of pi would make the sine of x equal to 0 and would hence make this equation true. Then over here, this is cosine of x equals 1. Again, on that one I happen to realize that cosine of x equals 1, that's when it's at its highest point. Right, cosine gets up as high as 1, goes down to minus 1, back to 1. That is, by looking at the graph here, I see pretty clearly that I'm at the tops of the tops of the bumps there. So that happens at 0 and at 2 pi and at 4 pi and at negative 2 pi. So it looks like here x is 2 pi n. Which actually, I think this is not new information. That is, this has all of the pi's and this has the even pi's. Right? Anyway, the idea here is that on some of these you're going to want to factor, get everything over to one side. Try not to divide by a trig function, because if you divided by 0 you just lost information. Alright, I think that's good for this video. I'll do another one with a few more examples in just a moment.